Sir, sir. Sir, sir.
సార్ కి వినిపిస్తున్నట్టు లేదు సార్. ఆయన
I think some
shall we start, sir?
Sir, some voice is coming out. Please check it.
Yes, sir. Sir, mute mode లో పెట్టుకోవాలి. Sir, mute లో పెట్టుకోండి. Sir.
Malay sir, please start the program.
Yes, sir. Good evening to all participants. On the occasion of 137th birth anniversary celebrations of Sri Srinivasa Ramanujan, our department is conducting a one-week online international workshop on mathematics, bridging ideas and innovations MBII 2024 from 16th to 21st December 2024. On the first day, that is 16th December 2024, Dr. L. Jagannathan sir, Professor, School of Computer Science and Engineering, Vellore Institute of Technology, Chennai, delivered a talk on mathematics of machine learning. On the second day, that is 17th December 2024, Sri NVRD Kumar Garu, Senior Faculty, Department of General Education, Skyline University College, Sharjah, United Arab Emirates, delivered a talk on lifelong learning in the era of AI. Yesterday, that is 18th December 2024, Dr. T.S.R. Murthy Garu, Professor, Department of Mathematics, Sri Vishnu Engineering College for Women, Bhimavaram, delivered a talk on some aspects of statistical hypothesis verification. More than 500 participants attended yesterday's session. Thank you one and all for your valuable participation in yesterday's session. Now, I request our beloved head of the department, Dr. KVLN Acharya sir, to address the gathering for today's session.
Good evening to all. Respected revered resource person, Dr. P. Nagarani Madam, my esteemed faculty members and dear beloved students. We are all gathered here through virtual mode in the fourth day of our international workshop. All of us know that the computation skills of mathematics, along with the conceptual approaches, definitely enrich the students for enhancing their knowledge in multifarious fields. In addition to it, it also helps us to update existing knowledge in the student community and create a deeper interest in various fields of mathematics. I appreciate all our students for their active participation and interest towards enhancing their knowledge. Today, our resource person is Dr. P. Nagarani Madam, Associate Professor, Department of Mathematics, the University of West Indies, Jamaica. Madam did commendable research on fluid dynamics under the able guidance of Professor G. Sarojama Garu from Sri Padmavati Women's University, Tirupati. I am sure that Dr. Nagarani Madam's ability not only captivated the attention of our students, but also deepened students' understanding. Her inspiring character, motivational behavior, teaching abilities, research capabilities, extraordinary communication skills are additional qualities in her, apart from his goodness and vast experience in the field of education. Definitely, her knowledge has to show significant impact on our students. Hence, I feel privileged to have such a good resource person today with us in this section. Thank you, Madam. Thank you very much for accepting our invitation. Finally, all our students for their continued enthusiasm and dedication. I am sure that today's session will be a fruitful one with a learning experience, both enjoyable and enlightening. Thank you one and all.
Thank you very much, sir, for your valuable message. Today is the fourth day in our one-week online international workshop. Today's speaker is Dr. P. Nagarani Garu, Associate Professor, Department of Mathematics, the University of West Indies, Mona Campus, Jamaica, West Indies. Now, I request one of our staff organizers, Mrs. K. Nagamani Garu, to present profound profile of Dr. P. Nagarani Madam.
Good evening all. Welcome you all to a one-week online international workshop on mathematics, bridging ideas and innovations. It's my privilege to introduce today's resource person, Dr. P. Nagarani Garu. Dr. P. Nagarani Garu is a senior lecturer in mathematics, specializing in applied mathematics at the University of the West Indies, Mona Campus, Jamaica, West Indies. She also served as head of the department for the last 6 years from 2017 to 23. She did her BSc from Acharya Nagarjuna University, MSc, MPhil, and PhD degrees from Padmavati Mahila University, Tirupati, AP, India. She is a recipient of several awards and medals for her excellence in her education. At UWI, besides her teaching, she has introduced several programs and several undergraduate and graduate courses. She has guided many students at master level, guided several MPhil and PhD students, and also visited several institutions around the globe. So far, she has published 34 research articles in international journals. As a teacher, she has received awards for outstanding achievement in teaching from UWI several times and also received awards for her publications. She has received a Young Scientist Award for the year 2016 by the World Academy of Sciences and CAS. Selected as a distinguished young woman scientist from Jamaica by the Inter-American Network of Academics of Science for the year 2015. She is a fellow of the Caribbean Academy of Sciences and a life member of the Indian Society of Theoretical and Applied Mechanics, Andhra Pradesh Society for Mathematical Sciences, and Indian Mathematical Society. She is a visiting professor of for several universities. She also served as a reviewer for several journals in her area of specialization. Besides all these activities, she actively participates in various activities, especially for girl education. She is also very active in alma maters and has been greatly contributing to the school where she studied and her village. Thank you, one and all.
Thank you, Srimati Nagamani Madam, for your nice introduction about Dr. P. Nagarani Madam. Now I hand over the session to Dr. P. Nagarani Madam. Madam, please.
Thank you. Thank you, sir. And thank you, everybody, for a kind words. And always, whenever we hear these things, always we feel like we have to be, more responsible and more creative, more innovative. Thank you so much. First, I would like to thank the organizers and especially who has been pushing me to participate in these seminars, even the early hours. This is 4:30 in the morning now. So, and always what connects me for though it is a difficult, sometimes in the night, because the roots, where I came from. When I say Nagarjuna University, I felt so good. So this is how it is connected. And I'm very happy that, especially Dr. KVL and Acharya Garu and Dr. P. Vijay Sarade Garu continuously, in touch with me asking. But I'm very, very thankful. And even entire team who has been involved in this workshop. I'm very much thankful, and this is my second talk, means which is the last year also. At the similar time, same time, I have given a talk. I was very, very happy with the response which I have received, and that's why on those lines I planned a talk. Which because if some students who has already attended that lecture must be get something more details into numerical methods. So once again, I'm thanking each and everyone for your encouragement and also involving me. Thank you so much. So with this, I am going to start my presentation, and I'm very happy to hear any questions, even at that time, if they raise their hand, or otherwise even at the end. And let me begin my presentation now.
Thank you, madam.
Yes, madam. Yes, madam.
Yes,
Your
sir.
screen is
Please.
clear, madam.
Yeah, anything is there, please let me know, sir. I cannot see the other screen. Thank you.
Yes, madam. You can carry on.
Okay, thank you. So now I'm going to do a little time on numerical methods for scientists and engineers. But if some of you have attended my previous talk, I spoke about mathematical modeling in engineering. where we have seen several problems, and those problems in reality, okay, we are unable to solve simply using analytical methods. Therefore, the importance of numerical methods were discussed in the previous talk. So I'm hoping who has attended nicely connect the link. And also, I would like to say something about the workshop. I have seen the all the various aspects, components that are presented. I find it, they are very interesting. I'm hoping that, this will also enhance you or add you something to your, okay. So first we will let us talk about why we have to be doing numerical methods, and especially as engineers. I know you're all engineers. What do you want, and what is the essential elements when you are learning, okay, to understand better and apply, and when you're simulating the models. So what are the important aspects of numerical methods one need as an engineer or as a scientist? So, what we do in numerical methods, basically, in numerical methods, so these are the methods. Okay, what we do is we determine approximate solutions. Okay, you know that numerically, when you are solving a problem, okay, you don't get the exact value. I'll explain why. And you get the approximate solutions by using some mathematical procedures. This is very, very important to understand that. Okay, so the mathematical procedure is important. Why? Because especially when you're solving, okay, your problems numerically, so through numbers, whatever the machine you are using, whether it is a calculator or whether it is a computer, so the capacity of those, whether a calculator or computer, can accommodate, particularly when you see the decimals, only up to some decimals on maybe 6 or 7. Therefore, always you can see how much better method you used, because always you are neglecting some component, some element of each calculation. So you can clearly see where, okay, it deviate from the exact solution. And also, while going through this, you can see even the method that you are going to derive also, you are not going to take the complete components. There are a lot of truncation happens. So because of all this, the methods, the solutions that you get are approximate solutions. And but okay, those are the best representing the situation. So, what are the applications of numerical methods? Then you must be, I heard, okay, in the first year, second semester, you had a course, but I'm sure you have gone through. I am not sure how many techniques or how far you have been. So, but I'm hoping even you have learned, so you can see some of the different aspects in terms of analysis also through this talk. So different problems, whatever in a reality, in real life, whether you in any mathematics textbook so far you did, all those problems where you see difficulty, then you can go to numerical method and solve those problems. Even from the, okay, childhood, whether you have done a root finding methods, or sometimes if you are unable to find the derivative of a function and integration of a function, what you can do them numerically. Or maybe you have solved some problems, in matrix analysis, solving the linear system. But if you wanted to solve that, okay, numerically, okay, that can be done. And also, when you have a nonlinear systems, and that can be done. There are number of methods. You can solve differential equations, and there is a curve fitting, and all these where you can see your numerical methods can be applied. But what is the one important aspect one has to understand as an engineer, first of all? So, what is the difference between analysis and numerical methods? So, when you are doing numerical methods, you should be not neglecting or ignoring the analysis part, because these are the methods that are derived from the mathematical analysis. Suppose, for example, if you are applying a root finding method, you should know whether the root is there in the interval or not. And also, suppose if you are applying the methods to solve the differential equations, and we have to understand about the uniqueness and existence, and also you have to understand the stability concepts. So the mathematical concepts are very, 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 very important in order to apply numerical methods. Was so often what I have counted is, suppose if you have no knowledge of analysis, even anyone, if we don't have a knowledge of analysis, we just learned numerical method as a simple step. We call it as an algorithm. Okay, so we are going to see a problem when you are applying for a large scale, especially in a real life situations. You will be seeing your problem is very complex, and you will be seeing that very lengthy and sometimes very difficult to solve. So in that case, in order to apply that technique to several problems, it is very much essential to know, okay, numerical analysis, because the analysis part gives you a strong background for, okay, your numerical methods. Therefore, one has to understand the analysis and come with the method and then apply. And then analytical methods versus numerical methods. So why you have to go to numerical methods, but still there is an advantage of analytical methods? Why people are tending and still some people strict to analytical methods? Normally in analytical method, what we do, you will get an expression. Okay, you are able to solve nicely. And suppose if you are solving a for example, a differential equation, and you will have an expression, so nicely it gives you a lot of information about the behavior. And even if one parameter changes, the same method can be, same expression can be used, simply you are changing the parameter. Okay, so therefore a lot of information we get from analytical methods. But when it comes to numerical methods, what happens is, so first of all, you are missing that form of a general solution, which is means in terms of different variables. Because if you change a variable, you have to apply the method and you have to solve the problem, and a lot of generalization components are missing. But okay, why we have to go to numerical methods is, as I said, in analytical methods, it is very, very difficult, okay, to find the solution all the time. For example, if you are solving an equation which come across Bessel's equation, I'm sure you must be using a lot of all those things. Okay, so there may be a lot of difficulty to solve this problem. But what we do, we wanted to go to numerical methods. And also see, suppose if you are solving a problem, maybe some people are doing optimization techniques. If you are doing an optimization techniques, and if you are working on a problem in an industry, okay, where you have several components of elements that you are producing. Let us think of a production unit. So you have 10 items are producing, and you wanted to, okay, analyze how best you utilize the resources. Such times we, handling 10 variables is not easy analytically, but numerically, nicely one can be doing. Okay, so that is how we use numerical methods. And also see, because there is a lot of development in now in when you are using numerical methods, as I see, mostly you are calculating. That means either you are using a calculator if you have like one step, two step, three steps, but it is very difficult even for a calculator. Then you go for some, okay, aid of the computer. Therefore, and the aid of computer is very important. I know in engineering you spend a lot of time, okay, and even might you have a lot of courses on computational skills. But it is very, very essential to understand and to have the knowledge of computational software, especially because of the development of the computers. It has applications of numerical methods became very easy, convenient, and also effortless. Therefore, one must have to have some complete knowledge of certain packages or software where you have the, okay, numerical methods can be applied. Particularly, there are a lot of software in maths which we use: MATLAB, Mathematica. So all these, a lot of functions are built in. So, and sometimes even for numerical methods, direct lot of packages are available in the internet. You can search it and see, instead of writing a code also, now it is available that you will be using those and solving the problems. So therefore, the aid of computer and development of computer added so much for the advancement of numerical methods. But also one has to know that the numerical methods is what you see is a very advanced course. It's going on continuously. Okay, the methods that you see yesterday and you can see some development tomorrow, still lot of research is going on, and you can see always scientists are trying for a better method every day. So you can see while solving the problems, while I'm analyzing the methods, you can always think, oh, that is another method which is a better method, means in terms of the better approximated method than the methods that we have used. So the history of when it comes to the history of the numerical method, see, it is not something, as I said, it is advanced. It is still actively going. Every day you are seeing lot and lot of numerical methods are coming. Latest methods are coming. But when you go back to the history, okay, it was very from long time. It's more than 3,700 years ago. So it is shown that the Babylonians knew how to find numerical solutions of quadratic equations and approximations to the square root of an integer. And you can also see, okay, an example of method of solving system of linear equations that we know as Gaussian elimination, which is still a very strong method, appears in a Chinese manuscript from the Han Dynasty. And Chinese mathematician during the Sung Dynasty generalized the method of successive approximations to find numerical solutions of higher degree equations, even finding a logarithm, you can see, which was initiated in 1614 and revised in 1624. So there are even 17s, okay, Newton's method, Runge-Kutta methods, all were, okay, developed and advancing, progressing. It has been happening. So as I said, the latest developments, yeah, as I said, so there are so many methods, so much advancement is happening day by day. So one can, understand and see what are the appropriate and best methods that can be utilized when you are solving problems. Oh, when it comes to the classification, normally, okay, numerical methods, we classify them as direct and iterative methods. Now, what do you mean by direct method? Means a direct method is simply gives a solution in a like a singular multiple steps as a like for a particular answer. Say, for example, if you are solving this problem, you can see by elimination, I can get x1 equal to something and x2 equal to something. Basically, x1 equal to x2. So that is a sort of a direct method. When it comes to iterative method, I cannot give something x1, x2, but what I'm going to do, I'm going to say x1, an approximated root, first approximated root, second approximated root, third approximated root, x2 first approximated root, like that. So therefore, and you get the sequence of such approximations, and that is what you call it as a iterative method. Okay, so in this case, I gave this example. One can see, okay, you have a function f of x, okay, and can be obtained. The root of this function can be given in this formula. So which I have applied the Newton's method, Newton-Raphson method, just to see the formula. Your x value, which is the root of this equation, is approximated. The nth approximated root is in terms of xn minus 1. Basically, you can see you have produced a sequence of approximations. So therefore, you wanted to understand several things here. Okay, when you produced a sequence of approximation, this is a recursive formula or iterative formula or an algorithm, whatever you call, then what you have to do is you have to understand whether that method converges or not. Okay, and whether those successive approximations approach the true value. What do you mean by convergence means? Okay, whether particularly Okay, for what value of n or n goes higher and higher, you at least you expect that is nearer to your exact solution. So that is a very, very important aspect in convergence, okay, in analysis. So, and also we have to very clearly have to have an idea of when do we stop the process. That is what condition we use to determine the iterative method to stop. This is very, very essential. There are several times in order to evaluate the stopping conditions, we may be going the error analysis by finding absolute error or relative error. Suppose in this case, particularly for the case of this function f of x, we will find f of xn. If the f of xn tends to 0, that is the root means, f of, say, for example, x star is said to be a root. If f of x star, for that x star, this value is 0, right? So therefore, your f of x star, where that x star value is 0, means even f of xn tends to 0, we will stop. But the thing is, you have to understand very clearly when you are solving a problem in a bacteria, okay, analyzing the growth of a bacteria in a lab or those problems, you are solving a problem at a scale of 10 power minus 6, 10 power minus 7. Those means you expect your x is in the form of 10 power minus 6, 10 power minus 8. So when you are analyzing in this case, you have to very understand that, okay, I'm sure when you're solving the absolute error, for example, which you find the difference between the original value and the exact value, even if you find the error going to be in terms of 10 power minus 8, 10 power minus 10, therefore that should not be indicating your stopping criteria. Therefore, you have to be very careful when you are applying the stopping criteria, whether you have to use absolute convergence analysis or relative convergence analysis, or whether your function tending to, okay, 0. So one has to give the attention to these okay, analysis when you are applying the numerical method, particularly in this case of root finding. You can see that. So what are the issues when we are solving problems, okay, numerically? And yeah, we have discussed why there are some issues, but still we use, because it is very difficult to solve that problem analytically, to handle it. So that's why we are going there, using it, and we are taking the aid of computer and we are solving. But what are the primary issues that any a scientist or engineer who is using these numerical methods can come across is the computational effort required and the accuracy of the resulting solution. These are very, 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 very essential. So in some of the problems, people are, work for several hours. And if you have a parallel computing facility, you will sort one component in one computer, one component in computer. So you can, save the time. But the amount of computational effort, so which is very, very important to analyze, and the accuracy of the resulting solution also, which is a important aspect one has to be considering. So when you are using numerical methods, one would expect, as I have mentioned, numerical methods gives you approximated solutions. So that means there are several errors that are possible. Okay, those errors can come from the formula that you are using, can come from the procedure that you are using, can come from the machine that you are using. There are several types of errors one must be aware of possibility when you are applying the numerical methods. So, especially as a scientist or engineer or mathematician, whoever doing using applying numerical methods, especially when you are in modeling, you come across several errors other than even the errors that come across through numerical methods, because especially when you are modeling, if you have taken the data, not exact data, and when you make some assumptions, there are so many errors, that can, entirely spoil the your simulation, your model. your complete analysis. So those are possible. So I'm not discussing those errors right now, but other errors in numerical methods is okay, common errors. We classify them as round off errors and truncation errors. So the round off errors is, as exactly I mentioned so far, that when you are using any machine, whether it is a calculator or a computer, it perform only to up to certain level, means it can store the information up to only, particularly in terms of the decimal places. When you see, it can store only some decimals. So that is how in each calculations, okay, as I said in the iterative method, first step you have some round off error. So second the calculation means when you go to second approximation, you will get another error. So therefore, these are growing the errors. So one can see, okay, such type of errors due to the machine, okay. So because it has only capacity of storing a finite number of digits, so that cause round off errors. And what are truncation errors? The truncation errors also very automatic, actually natural, because when you are solving most of the cases, the problems, you don't solve the complete equation. Lot of times you truncate it. Okay, so what exactly I can explain in a better way is, you can see I am finding the sum of infinite series here, but manually or theoretically, okay, so this I'm saying, but when I have to do in reality, I should stop my n somewhere, capital N somewhere. That is what you see, that stopping giving me that, I can't go infinite, and one person go n equal to 10, another person go 20, another person 30, but still you expect there is some error, and that means you are truncating, okay, at those terms, okay, that is called truncation error. But in general, you will be seeing in your numerical methods, in deriving the formulae, mostly you are going to use, in a lot of cases, you are going to use um, Taylor's expansion, right, for the function. So in that case, you are truncating, and then because of the truncating the formula in approximating a function, so you will be getting the truncation errors. So one has to aware of these errors, and one have to understand how to, okay, eliminate or reduce these errors. Okay, so I don't think, I have to spend a lot of time here, because a lot of people, especially you have done some, or maybe going to do some more techniques later. But let me revise, and so that you can see when I'm applying some models, you can beautifully see where these models are applied, and okay, how, and means other than solving a simple problems, where you can see these models can be applied. So there are several methods which you will use in real life, especially when you're solving problems. And these very commonly come across root finding methods. And the root finding methods are several methods: bisection method, regular falsy method, Newton raption, fixed point iteration, and all these methods. There are so many methods, okay? You must have learned also. But one can think, in the bisection, what you do normally, you bisect. Suppose if you know a function has in the root AB, you bisect that interval. Okay, especially see, the basic idea of bisection is intermediate value theorem. So once you understand intermediate value theorem, if your function is continuous function, changing positive to negative, there should be another, you have a zero in between A to B. So that is what you are using. That is where the analysis part comes. Okay. So therefore, you will be finding, you are bisecting that interval, and you are dividing that interval into half of the interval, and you are finding, okay. And again, you keep on in bisecting, and you will reach a point, and then you can see how, okay, nth approximated root is, and how best, and where to stop, you can decide. Okay, that is what is the bisection method. So, and there is a regular falsy method also. And bisection makes you, and these two called bracketing methods, where you have to give some interval, where you have to know and a root is. Therefore, always you will be bracketing the root. So where it is. So between A to B, you will be moving around. The regular falsy method also uses a sort of similar technique, but a regular falsy method, it can be derived using the tangent form. So basically, you approximated, okay, using a tangent form. So the regular falsy method formula can be obtained. And the Newton's raption method is, there are several ways to derive Newton raption method, whether you can use Taylor's expansion to derivate for approximate the derivative, one can derive. So you must have learned, but try to understand. And there is a fixed point iteration method. What we do is, instead of finding a root of a function, and we will find the fixed point of another function, okay, and then we link between root and a fixed point. So why there are several methods? That's why I wanted to give you some idea here. So here, especially in the root finding methods, okay, all these methods that I have spoke here are iterative methods. So therefore, when you have iterative methods, there is lot of things, your xn that have determined, which is the nth approximated root here. How fast it is converging also very important, because I said your computational effort, okay, one has to be considering while finding, okay, while applying the numerical methods. Therefore, in this case, you are finding a root, but which method you are applying, and how fast it is converging, that is also very important. That is where, okay, you have to know different methods and see the either rate of convergence or order of convergence. And first of all, one has to know whether these methods converges or not. In this way, the way I have arranged bisection method, as I said, it converges because it's completely in the interval, I have explained. So Newton raption method, so the convergence analysis. Okay. And if you have missed already anything, please try to understand. So the Newton method also, there is a theoretical aspect says once a function satisfies certain rules and regulations behaved well, for any choice of initial approximation, one can nicely apply the Newton raption method, means it converges for any initial, okay, root. So the rate of convergence and order of convergence are very important. The rate measures how fast it converges. As you say, as the faster it is, that means it is a better method. For you, like if I say rate of convergence is 2 and rate of convergence is 1, I wanted to go for rate of convergence 2. So in this case, bisection method is a convergence at a rate and order of convergence. Both in sometimes we use, simultaneously these words. But order of convergence normally we use in terms of the speed. Rate of convergence we use in terms of error. Sometimes in some books they are using, alternatively. But one has to understand. When it comes to bisection, it's a slow method. Its order of convergence is 1, but Newton raption is 2. So, and only when you're applying Newton raption method, the problem could be, if you remember, it has f of x by f dash. The derivative has to find. In reality, finding a derivative is also analytically is a problem. Therefore, so the complexity of Newton raption method is especially when the denominator f dash x is 0 and f dash x is small. And also what could be the another issue is when f of x is a very complex form and you are unable to find analytically, then again you have to take the aid of some numerical technique. So therefore, that is some of the, okay, disadvantages or difficulties when you're applying Newton raption. But if you, okay, so one has to know, okay, all these things. So, but that can be even, explained. You can replace this method with the secant method. Derivative can be, okay, used. So in terms of the difference terms, okay, that also secant method can overcome. But when you are applying the secant method, there is a possibility that it may not converge. So one has to be very careful when you're applying these methods. So the important aspect is convergence, rate of convergence, order of convergence, and also you have to understand which method you are applying. And also there are several methods, accelerated methods also, how to accelerate also. So there are a lot of methods are okay. So there are different methods, okay, when it comes to numerical differentiation and integration, because we come across in real life when you're solving problems also, maybe you are come across lot of problems where you have to find an integral, maybe particularly integral I see a lot. So you must be using all these methods, Simpson's rule, Simpson's 1/3, okay, Simpson's 3/8, composite, Gaussian quadrature and all. Okay. So I'm sure you have that idea. Maybe I'm trying to give some analysis part so that it would help you when you are applying these methods. And also what are the elements there is a possibility to miss. Okay. That is something I wanted to here to give in this talk. So the numerical differentiation basically, so sometimes it is very difficult to find the derivative of a function because a function could be involved complex terms, you have a special functions involved. Imagine, you are working on a complex scale, uh, in special functions involved or otherwise integrals involved, and that is very difficult to find a simple formula. What we do in those cases, we use interpolation. Okay, what exactly interpolation is? So particularly in a polynomial interpolation, you interpolate means you have a construct a polynomial, okay, to approximate the function such that your function and the polynomial takes the same values at some points. That's what normally we do. That means it's a very easily we convert the function to a polynomial. Once you have a polynomial, it's very easy. You integrate or you differentiate because polynomials, happily, infinitely many times you can integrate, differentiate. We have the idea of their behavior and all. That is the advantage of interpolating polynomial. So that is what we do in interpolation. So when you are differentiating, so we use those interpolation polynomials and then use it now. Okay, you differentiate the polynomial first time, second time, third time. That's what we do in a lot of cases. Also, we use finite differences. I think I have some derivation parts for finite differences because the real life problems I used finite difference. That's why, okay, I'll show you the formula. So normal in a finite difference, what we do is the derivatives, what we have, we write in the form of the differences. So in terms of the function differences, okay, say for example, if you have f of x, so you are going to change it to f of x plus h minus f of x, something like a differences. That's called finite differences. So these are some of the methods. And numerical integration is, very, very, very important. You must be using, okay, here also note that trapezoidal method, Simpson's 1/3, Simpson's 3/8 method. And also you should be knowing the error analysis, how much is the error is growing and what is the error. And basically another concept you must be seeing it. Normally what the basic idea of trapezoidal method is when you are approximating a function means you are integrating. Maybe I should have some marker to write integral a to b f of x dx. You approximate the function with a simple linear polynomial here. Okay, in the trapezoidal rule. Okay, so you approximate a function with a simple trapezoidal linear polynomial and you integrate it. That's what is a trapezoidal method. So in Simpson's method, you approximate the function with the second order polynomial, which is the degree 2. Then you approximate means you divide the interval into 2 intervals. So then you apply that, which is called Simpson's 1/3. And 3/8 rule, what you do, you approximate the function with the third degree polynomial and integrate. Those are the methods. That is how they are derived. In the composite formula, what you use is you use these formulae, what you derive into number of smaller intervals and you use them. Those are composite formulae. Because what one can think is, why can't I apply the nth degree polynomial at a time if I have n plus 1 data points? Because there is a possibility that it oscillates, there are oscillate from the original solution. So errors are, more and more you have to understand. So therefore, okay, that is what we use the composite formulae. And also we neglect it by using spline interpolation. I'm not sure you must have done, but it's a spline interpolation also. What we do, you divide each piece into smaller piece and you apply the integration techniques. That's called a spline interpolation. There is a Gaussian quadrature also, which also we use, okay, where several formulas are derived, but the Gaussian quadrature is very useful, especially when you're solving problems whose geometry is not in your hand. One has to understand. In trapezoidal Simpson's rule, you need to be knowing the endpoints. You are using the endpoints of the interval. In the Gaussian quadrature, you don't need to specify where the interval. Within the interval, there are some points we use. So that is the advantage of a Gaussian quadrature. So these are something, which we need to be understanding. Similarly, you will be solving several problems where you come across linear systems, which is Gauss elimination, Jacobi method, Gauss-Seidel method we use. Because I said one simple example in the linear optimization problem, simple problem, any problem when you take, or when you're solving a problem with 10 items, you have a 10 by 10 matrix, it's very difficult to solve. So therefore, Gauss elimination is there. But Gauss elimination is still, gives you approximated solution. But the thing is, in Gauss elimination, you need a lot of computational efficiency, time. So that's why sometimes we go for another iterative methods. Jacobi and Gauss-Seidel methods are iterative methods where, because in a lot of problems when you're solving in real life, you come across linear systems, and then we use all these models. Okay, so where you have these linear systems can be solved. So in reality, okay, there could be a lot of nonlinear systems also where you solve them. There are several methods: fixed point method, Newton's method. So these are the methods which we use in order to, and also this linear system not only come in as it is like as a direct problem, but when you are solving differential equations in terms of finite differences or in terms of finite element method, you come across these equations. Who has been using, who has been reading, must have an idea. So you need strong understanding of these methods. Okay, so I'm going to spend a lot of applications in terms of the numerical, in terms of the solving partial differential equations. So that's why I want to give a little idea about differential equations, some methods, and then I'm going to show some real examples what we are using, where you can also link, the advantage of the numerical methods, and also what are the problems, one can do. And you are really interested in your projects also, you can take some projects, where you have a combination of maths with computers and with numerical techniques are involved, which is going to be a wonderful work. So in reality, when it comes to modeling, I have explained previously also, most of the cases if you're dealing with the continuous models, so it's quite obvious to see that every time you wanted to see the rate of change. When you have that rate of change, if you are talking about your differential equations come into picture. So lot of phenomenon you must be, whether you are electrical engineer, mechanical, chemical, biomedical, all fields, you must be seeing some processes you come across the derivatives. So therefore that is where you wanted to understand, the differential equations and how to solve them, and the theory, it's very, very important. And also, when you are applying numerical methods, classification is also very important, especially see when you are applying the numerical methods for partial differential equations, and the type of equation is important so that you analyze the errors, you analyze the stability in a different way. So when it comes to differential equations, whether you have a ordinary or partial, you classify them as initial value problem or boundary value problem. When you have a time derivatives in partial differential equations, we call them as both initial boundary value problems. Basically, it has a time which changes with the time, and boundary means changes with the boundary in terms of the geometrical coordinates, which is xyz. So normally, in general, what do you mean by initial problem? Initial value problem is you have a differential equation with the conditions are given at a single point, whether it is a first order, second order, third, or the nth order. Your information is prescribed at a single point. What could be that single point? Normally is the initial point in the time, which could be t naught, doesn't need to be zero, okay, t naught, or it could be initial position in a space, which could be x naught. So something like that. You see that? So when the conditions are given at a single point, we call it as a initial value problem. And so when you have a boundary value problem means, okay, a differential equation with the conditions are prescribed at more than one point. So therefore, it simply deviates from here to this. Conditions are given more than what one point. It is not saying anything about where these points has to be given. Normally, see the simple, quite nice example I gave here. Suppose if I am solving a problem from 0 to pi, therefore my boundary conditions are, 0 at 0 is given, pi is given. I gave some simple condition, but doesn't need to be at the end point. It could be any point. And it doesn't need to be even like a 2 boundary conditions are given. It could be 3 boundary conditions are given. So boundary value problem theory is very, very, very interesting. And you come across boundary value problems in every field. When you're studying about any problem on the spatial coordinates, you come across boundary value problems. Therefore, it is very essential for you all to read some material on boundary value problem. Okay, maybe you must be, going through only a little bit about only linear boundary value problems, but non-linear boundary value problems, and these are very, very essential. So in most of the methods in the literature, you see, when you are solving these problems, there are several, boundary conditions. The problems with several boundary conditions are discussed. So the first boundary condition in the literature, you will be seeing them as a Dirichlet boundary condition. Normally, a Dirichlet boundary conditions means the conditions are prescribed. The unknown is prescribed at some value of the independent variable. You can see that. But when it comes to Newman boundary conditions, the derivatives are prescribed. When you comes to, okay, when it comes to mixed boundary conditions, you can see, okay, either or, whether it could be a function value or the derivative or a combination. See, so the combination of one with the function value, one with the derivative, we call it as mixed boundary conditions. And there are separated boundary conditions. This is very common in all problems, okay, which you are dealing in all engineering problems. Lot of cases you see separated boundary conditions mostly. Okay, the separated boundary conditions means the conditions, okay, at one point which was given separated from the conditions at the other point. In this case, you see the condition at y0 is separated from the conditions at y of pi. These are very common, but in engineering, I know periodic boundary conditions are also very common. So these are some of the boundary conditions are very common. So again, when it comes, you must be knowing a lot of methods to solve, but understanding the analysis part also very, very important. Here, the problem should be well behaved, well posed problems we call. So suppose, let us see, when you solve a problem, at the end you get a zero solution or infinite solution. That's a problem. Therefore, you have to understand, first of all, whether there exists a solution or not. there comes the existence and uniqueness. Once you guarantee the existence and uniqueness only, you can expect the solution behaved a nice solution. So whether there is a convergence concept is there, okay, whether the stability concept, all these one has to understand. Therefore, there comes the importance of existence and uniqueness theorems. Therefore, you have to understand, you have to know under what condition initial problem has a unique solution, and boundary value problems behave very differently from the initial value problems. Boundary value problems gives either zero or one solution or infinitely many solutions. Therefore, it is very, very essential to understand the existence and uniqueness of these problems when you are applying the numerical methods. Okay, so when it comes to initial value problems, there are several methods, which is Euler's method and its family. There are even the modified Euler's method. This is a forward method. There is a backward method. There are several Euler's methods are there, and Rangi-Kutta methods. And this is the fourth order Rangi-Kutta method I gave. So here there are different methods, and here are these methods of order in terms of when you talk about errors, order h square, order h power 4. These are the methods of order, different orders. So the h I gives you here the step size. Normally it is between 0 to 1. Therefore, as order h more and more, those are the better methods. That is how we see it. That is coming from especially when you are deriving this formula, you are using the Taylor's expansion for this function. So you truncated it, second order term. Therefore, one can clearly see here there is some error is involved. Okay, that is called truncation error. So similarly, Rangi-Kutta method, this is I gave the fourth order method because it's order h power 4. That's a fourth order method. So the formula here is, okay, you can see. So this is the scheme. Once you go to any textbook, you have all these formulas given and you are going to apply. But I would like to add something, when you are applying. So, and when you are applying these methods, it is very important to understand the concepts of consistency, stability, and convergence. So the consistency speaks about the local truncation error growth. So, okay, um, as I said, when you are deriving a formula, at each step, you are applying the Taylor expansion. Therefore, some error is there. Okay, so therefore, the method is said to be consistent when those errors are neglected when h is very small. So stability talk about the entire error, how the error growth. Normally, stability, when you any change in the initial data, for example, ya equal to a you have given, which maybe I have 1.0001 is my a, but other person neglected, 1.001 I don't want, it's very small. He might have neglected, she might have neglected. In that case, see, there is a possibility that the error can grow more and more. So that is what you talk about the stability. So because the element you take A is between 1.0001 to 1.0, you shouldn't be expecting your solution from you and other person should be varying and abruptly. Okay, that concept is dealt by the stability. And also the convergence, as I said, okay, whether the solution you obtain converges to the exact solution or not. That is the convergence analysis talk about. Therefore, when you are solving these problems, ordinary differential equations, so we will be very important to understand these properties and these analysis to apply. When it comes to boundary value problems, there are several methods. Okay, shooting method and finite different methods. So there are other methods also, collocation method, and you can see all those methods. So, and what we do, I think I'm going to focus on a finite difference method. But what exactly in a shooting method is, it's very interesting. In a shooting method is, okay. So what we do in a shooting method is Normally in a shooting method, you convert the problem, boundary value problem to initial value problem. That's how you do. Okay. So you keep on, finding construct of initial value problem and you solve it. And at the end point, you see whether that is about matching to the boundary other value or not. Okay. You can read it. So that's what we do in a shooting method. Okay. In finite difference methods, as I explained, what are when you are using a numerical differentiation, I have explained what is what are finite difference methods. Excuse me. Finite difference methods. Okay. So I give a little background because the examples that I am going to show, I used finite difference, I think finite element, which you see in a real life example. What normally you do in finite difference method is you divide the interval into small pieces. So I divided here number of intervals and step size. And what we do is we convert the derivatives in the form of difference forms. You can see this is what I am saying about Taylor's expansion. We use continuously all these formulae. Euler's, Rangi-Kutta, everywhere, we use Taylor's formula. That's very, very, very important to understand Taylor theorem when you are approximating the function. So the formula, you see, we derived. Okay, so this is called the forward formula. Basically, you are using one step forward. And you can see this is the derived from same Taylor's. This is called backward. So you're using one value, backward value, in order to find the derivative at the ith value, which is your present value. So this is the second derivative. This is what we call as a central difference, because in order to find the ith value, we will be using one step less, means backward, one step forward. So which is you are finding the value at the center difference formula. And also for the first derivative, you can see for the first derivative, you are using because the second derivative here is order h square formula. Therefore, when you are applying this on x, another first derivative also to be consistent. Therefore, when you are applying that, so you will be using a central difference formula with order h square. So this is the differential equation you are solving. And the boundary conditions I have taken here are, simply see Dirichlet boundary conditions. Therefore, now I think you are very comfortable with the language because I have introduced all. So these are the conditions. So Dirichlet conditions, function at this value is given, function at this value is given. So therefore, only my unknowns are now, because you have a total n intervals, therefore n plus 1 points. Therefore, n minus 1 unknowns I have here. So here to here, I have to know my function. That's what the aim. So when I substitute this, okay, all these formulae. So I use the second derivative, okay, which is the central. And to be consistent, I'm using the central difference formula for the first derivative. And I'm y at yi. So these are y at xi. I'm indicating it as y at a high. Y at xi plus 1, I'm indicating with the ya. That is the notation. So we have this is the, okay. So after substitution, you can see now I'm combining. So basically my unknowns are going to be in terms of I plus 1, I minus 1. So every time I have 3 unknowns. So I plus 1, I minus 1. So that is goes from I0 I know, IN I know. So I wanted to know 1, 2, 3 to n minus 1. These are the points I want to know. So therefore, so here you can see what happens. I gave one here, what happens when n equal to 4. And I have I1, 2, 3 is to be known because I know at I0 and N4, those are given A and B. These are given. So therefore, you can see Y2, Y1, Y0, Y3, Y2, Y1, and Y4, Y3. Every time you have only 3 components you see. It's quite interesting. You see, your Y naught is known. So therefore you substitute A. Your Y4 is known, you substitute B. So the first element and last element has two elements. Therefore, when you arrange them in a matrix form, you will see a tridiagonal matrix. Okay. So you are solving a tridiagonal system. Okay. There you use the, okay, numerical methods that we have mentioned before, whether you go for Gauss elimination, whether you go for Jacobi or Gauss Seidel. So that is what you use. So when you see in the form of a matrix notation, you can see you have a linear system and it has a tridiagonal system where you use the. Okay, so in Jacobi, what you do normally is, okay, in the Jacobi method, you want to find xi plus 1. This is the element. It is an iterative process. From the first equation, we will write what is x1 and we derive the formula. So every time that I plus 1, it will be in terms of y. Therefore, this is how, okay, you can scheme can be derived. And once you initiate with the initial value, in this case, say for example, 0, 0, then you continue for the first approximated solution, second approximated solution and all. Try to understand here, when I am applying this method, my A11 should not be 0, A2T should not be 0, and that should not be 0. Okay. So similarly, when it comes to Gauss-Seidel method, same thing. But what we do in Gauss-Seidel is, I know in the first step what is x1. When I'm applying for x2, already I know x1 in the same step. Therefore, I'm going to replace here with the I plus 1. That's what is the Gauss-Seidel method. So this is the Gauss-Seidel method, suppose if you are using. So x1 I plus 1, because x1 I plus 1 is known. Therefore, you will be using x1 I plus 1. Okay, you can clearly see this is the Gauss-Seidel method. So in order this method again to be convergence, it's very, very important, to be taken care. Once you are working in a long scale, if you have no idea of the analysis, again, it will be a trouble. It can be, chaos. So when a matrix is a strictly diagonal dominant matrix, so that is when you have a sigma A greater than 0. And with all that, you are assuming your A is a non-singular matrix in this case. When it is a your non-singular matrix only, you are trying the unique solution. Okay. So that case, once you guarantee that it is a strictly diagonal dominant matrix, those two methods converges for any initial approximation. So with that idea, so we can apply those methods and solve. That is what. Okay. So when it comes to numerical methods for partial differential equations, even, there are finite difference method I explained. So when I said the ordinary differential equations, we used only for one x, what is the finite difference. But similarly, if you have a y, z, t, all, you can use different formulae and you apply. So there are several methods: finite difference method, finite element method, finite volume method, based on the geometry you're applying. So these are where you can see which one is comfortable. And sometimes, it is very difficult to go for, in terms of solving the original equation to that order. So in the finite element method, we try to, go for reducing the order and then approximating, and then we use the finite element. There are several methods in engineering. You will be seeing a lot of methods. I know, okay, mechanical engineers must be having finite element course, I remember, but you can tell me later. So there are these methods, you apply, simulate your situations and solving different models that you have a continuous data. Okay, so with this, I'm going to show some more, maybe some examples, one or two, where you can see in real life where we are using. But with through some of the papers, some of the work that I'm doing, I'm going to show several of the numerical methods that I spoke were used, and you can see in reality, okay, where the need for numerical methods. So in this case, I'm going to do a little, no, maybe scientific more, but I'll try to give stress on the numerical methods. This is the problem where I'm doing, not going so much details, but I'm going to do, everybody know the convection diffusion process, I'm sure, because convection diffusion or diffusion in our heat problems, you will be come across whether you are a chemical engineer, whether you are a biomedical engineer, and even maybe in a heat problems and mechanical people, and maybe in a mechanical, you will be using the fluid mechanics, so you will be seeing several of the problems when you are even solving the flow, Navier-Stokes equation of conservation, continuity, all these equations you will be seeing. Okay, you will be using numerical methods. So when it comes to dispersion, here the word dispersion means it's a convection diffusion. You have a diffusion process where, particularly you have a diffusion and you have a convection, and you are solving a convection diffusion equation here. So this problem, when it comes, you can see what we are doing. We are solving this problem in an annular case. Normally, what we do in reality here is the application of this model for whether it could be a biomedical engineer or whether it would be even the chemical engineering. So this analysis used. Okay, so the convection diffusion problems has applications in biomedical engineering, physiological fluid dynamics, or else, in if you go to cardiovascular flows, or when it comes to environmental engineering and polymer process engineering, where you are mixing, so all that where you come across your convection diffusion equation. So you are solving a convection diffusion equation, you will see there are lot of material is available using the finite element, finite difference. It's very difficult to solve the convection diffusion, the entire equation. So we are using a convection diffusion equation. So therefore, you must have seen these equations. The basic idea of convection diffusion comes from your Fick's law and Fick's second law. So when you see it a one-dimensional equation. So the Fick's law, which gives you the relation between amount of flux. Okay, this is the relation. And when it comes to second law, you can see this is rate of change. So that is changing. D is the diffusivity coefficient. C is the concentration, which you call the local concentration. So these problems come across, as I said, in environmental engineering. So for example, in the engineering problems in reality, if you are talking about, suppose you have an industry, so suppose the pollutants you have to send out after a process, you want to send out the pollutants to out, so therefore you must be using some pattern. Therefore, that pattern, whether it is analyzed by the diffusion process, you can see a lot of work is available on those problems. So therefore, where if you are only talking about the diffusion means spreading, not taking care of any convection, then you can see, these equations come across. But if you are taking care of there is a convection, suppose your pollutants are transporting, suddenly a wind came, then you can see there is a convection process is also involved. In those cases, you have a convection terms also comes. Okay. So therefore, your equations looks like this. So when you are modeling, whether it could be a rectangular or whether it is a cylindrical coordinate, based on that, you write those equations. So you want to solve these problems. But in reality, so solving a problem means, especially we will be solving for a situation. Every situation, every model has some constraints. Therefore, we bring them those in the form of either boundary or initial conditions. So therefore, you have a problem, you wanted to solve that problem, okay, using those initial and boundary conditions. So, um, so um, this is the equation particularly I want to solve. When I use the cylindrical coordinates, this is so the example that I have projected here is you are studying the dispersion in annulus. This has an application, especially in biomedical engineering. In a balloon angioplasty, what they do, they put a catheter into the coronary artery and they push from outside so that any block or anything if they have, so they clear that or make some hole, so means peace. Okay, they clear that block. Okay, so in those cases these models comes, so where you can see, okay, in order to solve that, this is the situation. There are several methods were explained, basics from the beginning, but those methods are not going to helpful here for me in order to solve based on the situation that we have considered. Therefore we took the aid of numerical methods. So basically, as I said, the dispersion process you can see. So here is something you have, maybe think about a tablet in this form, and the unnatural diffusion makes them to spread around, left, right, because of the natural concentration gradients. But what happens because of the convection, so flow is moving here. Because of that, you expect that there is a shift. That shift is here. The shift is happening because of the convection. But once there is a gap here, automatically by natural process of diffusion, so the molecules are dispersing like this. That is called the diffusion. Okay. So this is a simple case where I consider it's going in unidirectional, which is in the axial direction. So therefore you see, okay, I have this equation in the case of axisymmetry. So this is the equation I'm trying to solve. I'm trying to explain, applications, through engineering in terms of, what we are doing, or in biomedical engineering, chemical engineering, all the, So the Taylor paper nicely explained, in chromatography, all these applications, especially in when you are applying the convection diffusion equation. So this is the equation we are solving. And so there are several approaches, but okay, in this method we are using a combination of these, but I'm going to stress on the numerical approach. So basically in this model we used a Kazan model, means the fluid is modeled as a particular non-Newtonian fluid. So okay, you can try to understand. And so basically, in order to solve this model, I need my velocity. So therefore, I'm going to solve both flow equations, which is equation of continuity, equation of mass and momentum. So those continuity equations we are going to use, and we want to go to obtain our velocity. So this is the schematic diagram. So this is what. Therefore, your catheter is inserted here. And see, this is the problem where we are studying. We are studying this, okay, whether it could be a food or it could be a drug, whatever, or it could be, the present model right now we are doing, which we just sent for communication, is the oxygen. When you have this situation, you have a continuous supply of oxygen after balloon angioplasty. So you are supplying the oxygen continuously to maintain after a balloon angioplasty. So we are trying to see the oxygen transport that is just now communicated. So basically it could be any drug, it could be any nutrients, the how those are moving axially. That is the process we are trying to understand. In engineering applications, see several problems. These problems occurs in chromatography, you can see, and even in the water purification also, there are so many, like membranes are inserted here. So those are the problems you can see come across in the these applications. So this is my equation. So we non-dimensionalized. The importance of non-dimensionalized, I don't think I need to say, but it is very essential, important, and make our life easy. When you non-dimensionalized, we make this model and you can apply, generate it and, apply for general cases without worrying about all the parameter scales when we are modeling. So therefore, the initial and boundary conditions are given here. So you can see this is the equation, and Okay, so my W is needed. So it is calculated from the um, equation of flow equations. So in this case, I have my W is very complicated here. Okay, it is going like a piecewise function. It goes from this form k to lambda 1 because my annulus, you can see, yeah, basically here it is an annulus because the Cassan had a particular property because it has in between like a solid behavior, means fluid moves as a single solid layer. Okay, so that is why I have a piecewise function, and you can see here. And so because I wanted to find where that plug like property for the Cassan fluid, those we call them as yield plane locations. Therefore in this case I wanted to know where the fluid has a plug like property, and the location where that ends in the middle we call them yield plane locations. That satisfies this equation. You see, this is where we are using again numerically because we don't know how to solve this analytically, and therefore we use numerically. I think we use the regular falsi method here to find all these positions based on giving other values. So regular falsi method is used to find the what are the lambda 1 values, and lambda 2 was find. Okay, now we wanted to find the mean concentration. Okay, so as I said, the approach here is the mean concentration is expressed as a series expansion in the local concentration is expressed in the terms of the mean concentration and derivatives. The problem is now converted into a problem of finding a mean concentration, because in a lot of applications we don't need to find targeting to particularly to local values. Okay, so we wanted to find mean values because through the entire annular region we wanted to. In engineering applications sometimes we don't care about even the concentration, and we must be caring about the rate of transport. So those are given by these transport coefficients. You can see now I have to solve these KIs, because if I want to find the mean concentration, I have to solve these KIs. Also, in order to analyze my rate of transport, I have to analyze my KIs. See, KIs involved here, I wanted to say there is some integral, complicated integrals, and W is complicated, complex. My Fi still has to unknown. See, this is where my numerical integration came. Okay. So this way where we used the Simpson's rule. Okay. This is where I wanted to solve my Fn. See, this is very complicated here because you can imagine here I have to solve my K and F simultaneously. That is only possible numerically because I have to assume when I am solving a Ti plus 1, my Ki I have to approximate it at what happens at Ti. I don't know at Ti plus 1. Okay, these are the simultaneously we are solving. Therefore, we use the finite difference method here. So we use the type of model which is called the Crank-Nicholson. In the Crank-Nicholson method, what we do, we use the average of nth term and n plus 1th term. So it's a finite difference method, you can see. Okay, and apply and we solve this. So what happens once you solve this, okay, these methods with Fn's, I can go my KIs, and KIs has to be solved again numerically. See, there are a lot of numerical work was done here. So once I know all these Fi's and Ki's, luckily what I'm seeing is my dou Cm by dou T is infinite series. Again, I have to truncate. This is the term, C truncation. So I truncated here. Okay, then the expression for Cm, we got it. But again, they have a lot of integrals numerically has to be evaluated. All these integrals are numerically evaluated because here my 0 to t, I know the initial value and end value. We used Simpson's rule. But if I don't have a control of initial end value, normally we go to Gaussian quadrature. So that is the scheme you can see. the finite difference scheme. Okay, these are the equations we have to solve, very complicated one by one. And we have to use the derivatives. Okay, we divided the domain, see the mesh in terms of t, in terms of x. So we gone from 0 to t, we gone from 0 to 1, this gone from 0 to capital T. We discretized both time and the in terms of the position. So R here, and then we solved. So it's very complicated. I think we go on for like 1000 by 1000 matrix or C. Okay, so these are I gave only simply for F naught. Same applied for F1, F2, and all. You can see again. I ended up with the tri-diagonal system nicely, and we have observed this is a diagonally dominant. So we applied. So I have to solve the linear system now. And in order to solve the linear system, we used Gauss-Seidel method. That's what it is explained. So Gauss-Seidel method was used here, and Ks are solved numerically, which we use the Simpson's rule. So these are done. See, a lot of numerical methods are very, very important here. So in the second model, I would like to give a little time. I have time. Little briefing about this model, where you can see the beauty of in different areas. Okay, so in this case we saw same problem, dispersion problem, but here the flow is different. It is called a peristaltic flow, but it's a beautifully explained. There are some videos where what happens is, instead of flowing here, the walls has the capacity to move the fluid. Try to understand, wall has the capacity. Okay, there are certain type of transport you can see in industries. Okay, even when they're mixing the materials in industry, they use this type of peristaltic pumps. Even in regular your labs, also in different labs, you must be using peristaltic pumps. So mostly what we discuss is biomedical applications, because I'm working on mostly in with those in my view, but same problems can be applied in any engineering where you see similar problems. So this is where I was telling, it has a nice wall itself, pushes the material. It has a property. Okay. So these are, okay, a particular type of the model. See, this is wall shape. Okay. So we used again Kassan model, and you can see, this is how it's a wall, it's a wall itself, moving the fluid like a wave. So wall has this shape, and this is where you want to apply your problem. You can see nicely. And these are the equations: conservation of mass, momentum, Kassan's I was saying. So these are the fluid velocity, and it is the axial here, because of the here in this case of the peristaltic wave, we have a transverse velocity also, which is V also we have, and volume flow rate. You can see now, this is again, we use numerical method here. So basically in this case, all these expressions, both velocity and transverse and axial velocities, are expressed in terms of the pressure gradient. So but the pressure gradient is involved here. And if you see, my RP is also in terms of the pressure gradient. My plug radius is also in terms of the pressure. So therefore, you have pressure term here, pressure term here, pressure term here. So it's very complicated to solve. Okay, analytically. So again, we use numerically to solve for P for given Q. I think we used a fixed point iteration method here. So we solved it, and then we got V, and then you got U. So by supplying Q, so then we come into the dispersion problem. So this is the problem we want to solve. So we simplified, actually. We are, sometimes it's very complicated. Even, to solve this problem, entire problem is complicated. So we used analysis and we neglected this term. So this is the equation we are solving. But because of the geometry, what we did was we used the finite element method. Okay. And also here we considered this problem has several applications, especially in drug delivery, particularly targeted to some regions. So there are several ways of how you have a form of the drug is considered also. We took it care. So there are, this is like a slug form. This is like, in the form of Gaussian distribution. So different forms were taken, different analyzed beautifully how when you give a concentration after a particular time with this process, how the concentration is there. So those are analyzed here. Okay, you can see now we use like 10,158 elements. We used a finite element method here. So finite element method, what we do is, I'm not sure how many people have come across this method, but I can give a little idea. Normally, we divided the entire region into small piece. In each piece, we solve the problem and we apply the conditions, and the problem is solved entirely. So this problem you can see like 10,158 elements were used. So each case we applied that and then we solved. You can see nicely, the distribution of the concentration over time was calculated. So, yeah, I think that's it. So these are the advantages of these methods. And I think I took a lot of time, maybe. I don't know. I really wanted someone to talk to me.
Thank you, madam, for your nice lecture on numerical methods for engineers and scientists. And this is the time for question and answer session. Because of participation, all the participants are requested to post their queries in Q&A box. Madam will clarify the same. And Q&A box is enabled and you can post your queries.
Yeah, even not the question, anybody can speak, anybody can say anything, because I'm not seeing anybody. So it's really good to hear from students if it is any useful, anything they learned. Because I don't know their level of numerical methods. So
Actually, students are
Nagarani
disabled.
madam,
sir.
Nagarani madam, really excellent lecture given by you, ma'am.
Thank you, sir. Thank you so much.
You provided an insightful overview on numerical methods and their applications. It is highly informative and enriched with valuable required knowledge for our students on numerical methods, ma'am. Moreover, your today's contribution has significantly achieved the objectives of our workshop and made today's section a fruitful one. Thank you very much.
Thank you so much, sir. It's my pleasure.
Thank you, madam. Thank you one and all for your good response and valuable support. Expecting the same cooperation for the remaining session also. Today's session concludes with vote of thanks by our staff organizer, Sri I. Potraju sir.
Good evening to all. On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. P. Nagarani Madam, Associate Professor, Department of Mathematics, the University of West Indies, Mona Campus, Jamaica, West Indies, who gave such a good and informative presentation on numerical methods for engineers and scientists. Despite of her busy work schedule, she gladly accepted our invitation and gave a valuable talk in today's session. Thank you very much, madam. I would like to thank our beloved head of the department and convener of this international workshop, Dr. Kevin Acharlu sir, who guided, motivated, and supported us to do this program and encouraged us to shape out today's program. I would like to thank our principal sir and our management, Bapat Education Society, for providing us all the facilities and encouraging us to conduct this program. Without their support, it would not be possible to conduct such a program today. I would also like to thank Dr. K. Mandeep Garu, Department of CSE, Institutions Innovation Council IIC members, Sri M. Lenin Babu, Faculty of ECE Department, Sri S. Prabhudas, Faculty of IT Department, Sri Shrikant Nalluri, Faculty of CSE Department, Sri A. Sai Kishore and Sri U. Venugopal, who are sincerely extending their technical support to us in conducting this international workshop. Thank you, one and all.
Thank you so
Thank
much,
you,
sir.
Sir,
And yeah, thank you so much. And really would like to hear
sir,
something.
can I end the meeting, sir?
Hi, sir, please, the resource person, madam is talking. Please wait.
Yeah, sir, thank you so much for this invitation. It's my pleasure to be joining. But I'm very happy if I hear any comments from the students even afterwards, because I would like to see it is something useful, at least, at least how it is impacting them. Is it useful or not?
Definitely, ma'am, madam, we will send feedback to you also.
Thank you. That
So kindly
really
extend, madam, kindly extend the same cooperation for our future endeavors also, ma'am.
Thank you, because it helps me, where they are. Is it something added or not? Maybe next time I should plan, more details into particular aspect. I really wanted to hear, sir. Even if
Definitely,
anybody,
ma'am.
from the faculty also, I'm very happy. But thank you
Definitely, ma'am.
once again, each and everyone, even the students. Thank you.
Bye, sir.
Sir,
Please conclude, sir.
yes, sir. Thank you, sir. I am ending the session, sir.
Please provide feedback link, sir.
Yes, sir. It is already provided, sir, in the chat box. And